Okay, this is more or less the third part of our course. And what I will do now is I would like to explain to you a little bit the role of L1. So I have a GeoGebra experiment which I will share also with you, but the main point of this plot would be you should understand why the Fourier transform of the rectangular function is the SINC function, and secondly, why this is useful and how it will lead you to the Riemann-Lebesgue lemma, meaning the Fourier transform goes from L1 to C0. So whereas bounded measures are mapped to bounded continuous functions, it's now that we are having decay at infinity or so. So, well, what is the Fourier transform? And keep in mind, I'm talking about the rectangular function, which you should view here as the function starting from -1/2 to +1/2, and with amplitude 1. So if you're going to do the Fourier integral, then you find out that this box function, I call it boxcar function, it's well, having a graph of area 1, the L2 norm equals 1, the sup norm equals 1, the L1 norm equals 1, and it's an even function, so it's flip symmetric or so. So if you integrate it against the sinus function, which is an odd function, you have an integral over an odd function over a symmetric interval from -1/2 to +1/2, and that cancels out. So what you have to do is, when you compute the Fourier integral of this function, is just look at the cosine term. So roughly speaking, this GeoGebra experiment, I mean, of course, you can do it more or less quickly by yourself, and you should try to do it. But I think we should have intuitive understanding why the SINC function is coming out and what is the behavior of the SINC function. So the SINC function, as we will see in a moment, is sinus of pi x divided over pi x or so. Okay, so what happens if you integrate a pure frequency, or actually a pure cosine function, over such a symmetric interval or so? And with the slider, you would be able to see how it's changing when you increase the frequency or so. But I'll try to discuss it without too much change of the screen. Now, what you see here is that depending on the frequency, you will have more and more positive and negative parts. But each full frequency, so each pair of up and downs within that interval from -1/2 to +1/2, will provide you with an integral, a vanishing integral or so. So assume you have now a high frequency with, I don't know, 12.5 oscillations per that unit interval. It means you have 12 times, or on almost 11/12 of the interval, you will have zero integral, and the remaining part will be at most this here. What is also clear, if you change those frequencies, and that's also nice to see. Yeah, you see here what I did here really is I was saying, well, take the cosine function, but then we take a equals 1 and can be changed from a range from very small to very big, and interesting is more very big. And then we are taking with this variable a, the cosine of this. So what I show you is a very low frequency 0.25 or so. Then I'm saying, well, integrate the function, and the yellow is determine the area of the yellow domain. If you increase the frequency, clearly you have more up and downs or so. And here the value is 0.13 or so. And then if you change this parameter, you see how it behaves. Now, what happens if you're choosing a to be an integer? That's interesting. And then you find out, well, then, let's say it's 3 or so, then you have 3 full periods within the unit interval. So within any interval of length 1, for example, the symmetric interval from -1/2 to -1/2 to +1/2, you have okay. you have integral 0, and that means the Fourier transform is 0. So that's the property of the SINC function. Also, if you change and you say, well, if you make it a little bit smaller or a little bit bigger, then you will see that it either has overwhelmingly positive or negative terms. So it's already clear that the Fourier transform, which is the cosine transform more or less of the rectangular function, will have zeros at the integers, except, of course, at the very first integer, which is 0, because if you take an extremely low frequency, like 0.001 or so, you're multiplying with an almost flat function. So in the limit, you will have just 1, so that's clear. That's the SINC function. Is also a consequence of de L'Hopital's rule. For other values, it will oscillate and will go up and down. Now, so here you have the formula that you find in all the engineering books. Is if you take the box function as the indicator function from -1/2 to +1/2, its Fourier transform as a function of x is sinus of pi's over s, and the pi is convenient here because it means the zeros are at the integers. It's alternating like the sine function, but it's decaying. So at every half in between, it's taking the values plus or minus 1 over pi over s. So the decay of this function is like 1 over s only. Now, if you take the Fourier transform, and the Fourier transform is really this mu of chi of minus s, but if you write it out, applying a measure with density f in L1, you immediately get that the Fourier transform is controlled in its subnorm by the L1 norm of f. Okay, and we will also see, and I would like to show you by pictures, that the SINC function is not integrable. So what I'm showing you here is that there's a part of the SINC function on the interval from 4 to 8. The SINC function is the blue curve. It's oscillating and with a decaying envelope like 1 over x or 1 over pi x, but with some peak values or so. But what you see is below this bump function, it's always possible to create an interval, kind of put a little box here of area 1 over 8 times pi, or I'm not sure, I think it's, maybe it's 8 pi, but that doesn't matter. But the point is, it's 1 over 8, it's 1 over 16 over a length of the double length. And if you increase it, you go from 16 to 32. It's repeating. The number of terms is increasing, but their sum is always adding up to something which is always the same constant. So here you have 4 times this number. Here you have 8 times this number. And so in this way, it's just 1/2 pi or 1/2 over pi divided by pi. Because you can do this as many times, the integral of the SINC function is plus infinity. It's a nice, decent function, but it's not integrable. How this works for multidimension is also clear, but you can also understand why this has to be like this. I mean, the non-integrability is essentially a consequence of the fact that the box function, which we have seen before, is having a cutoff here in the middle. So it has a jump. If you take an ordinary function which is integrable, so assume the SINC function was integrable, and assume that its inverse Fourier transform is computed almost like the forward Fourier transform. Since it's an even function, the flip operator doesn't matter. So really, the inverse Fourier transform is the forward Fourier transform. And therefore, we would have the claim that the box function is continuous. So it must be a non-integrable function. But I think looking at the graphs of the SINC function is a good argument to understand why it's so bad. Now, we had a discussion about the discrete functions here. And I would like to continue now with another property of, I'll leave out this and I will do this later, with the L1 property. Not using this for the moment. Sorry. Yeah, here. We have seen the dual space, and in this, or you have not seen it, I'm sorry, I will redo it. But I wanted to show you, yeah, this lemma. So one of the things that will be quite relevant for us later on is the existence of approximate units. Now, I see there is still something. So I have to be a bit wordy now and try to explain to you what I'm having in mind. So approximate units are a replacement for unit elements. We have seen that within the bounded measures, we have a unit element. You just convolve with the DRHO measure, which means you're shifting by 0, which is identity operator. If you have the bounded continuous function, of course, constant 1 is the right identity element. Constant 1 times anything is the same, the input function. But if you take C0, you have a problem. If you go to 0, you cannot recapture everything. But on the other hand, if you have some given element which is also vanishing in infinity, you can multiply it with a huge plateau function, and it will be, everything will be okay. So this is why we are talking about approximate units, and L1 is a standard thing where you have approximate units. Yeah, okay, maybe I try to share with another screen because sorry, I would like, yeah, here it is. I would like to go to the script, which is maybe more reliable, and recall things from the early part of the script first, and then make the statement about the approximate units in L1. So we have used a lot to go through this first. The translation operator, we can define it on many spaces. Sometimes we will also use the modulation operator, and it's very nice to check not only for ordinary functions, but also for measures, that modulation can be also called a frequency shift operator, because if you modulate a function or a measure, so you multiply it with the bounded continuous functions, and we can do so, then its Fourier transform will be just shifted. So a modulation operator is, on the one hand, practically speaking, a pointwise multiplication with a pure frequency, and S is the frequency parameter. S equal 3 means 3 full oscillations per unit interval, but it's also a frequency shift operator. Now, I think the dilation operator in line number 4 is the one which is more natural first. So if you give me any positive or even non-zero number, can be -1, then you can say dilation, or by a factor of rho of f, is you apply this transformation on the argument before taking the function values. So if you take rho equals 2, it means you're taking the values from twice as big arguments as you look at the new function. So DRHO f, if rho equals 2, shrinks the graph of the function. It preserves the value, the same values, but everything is shrinking. So in German, I would say D is for me a Drück operator. So it's a compression operator. In German, it's drücken und dehnen. So it's dilation, I would say. Now, there's another operator, and I don't go into the details now, but it's exactly the adjoint operator, and therefore it's well defined on the bounded measures. And that's the what I call stretching operator. Again, in German language, it's ST for stretching, strecken, oder stauchen. So if you give me a rho, which is, let's say, 1/5, it means everything is compressed. The graph of the function f, it's shape-preserving compression, but it's rescaled. So of course, 1/5 to the exponent -1 is meaning you multiply all the values by 5, which has the nice effect that it's area preserving. So we have two dilation operators which are adjoint to each other, And the dilations are isometric on the bounded continuous functions. They don't change the values, but they preserve the maximal value. And they are nicely compatible with pointwise multiplication. Whereas the stretching operator is preserving the L1 norm, or it's also preserving the norm. And it's allowing and making a change in the script. So here, rho small means you're shrinking the support. And that's exactly what we want to look at. What is the behavior if you shrink a function of integral 1? Now, dilation by a factor of -1 is our well-known flip operator. And you have a number of rules. We will derive occasionally some of them, but maybe not all of them, but you should know them. Skip the yellow one, but for example, if you multiply two functions, of course, shifting a product is shifting each of the factors. The same for dilation. Kind of you're replacing arguments by other arguments, and of course you do it in the product each term. What is kind of more interesting is if you stretch in the area preserving way a convolution product, you're getting the convolution product of the stretched operators. So that's a bit surprising maybe. And if you're not just applying a isotropic dilation, but maybe you're doing a rotation, it is interesting in image processing. You can convolve two images, but you can also rotate the convolution product by 45 degrees, which is the same as convolving in a two-dimensional way the corresponding rotated images or so. So this is quite easy. Yes, I have here the translation, modulation, and for our invariant for any norm, mostly for p equal 1, 2, and infinity. This one is area preserving, therefore only isometric in the L1 sense, and the DRHO operator is only isometric in the F infinity sense. So also again, I think it would be nice to have a GeoGebra plot and showing you how it behaves. Yeah, maybe the orange formula is important because it says if you modulate a function, or first applying the modulation operator, and then you're taking a Fourier transform of a modulated function is the same as taking the Fourier transform and shifting it. So again, I was saying this is a translation operator on the Fourier transform side. And if you would have a translation here, it would get a modulation, but with a minus because the inverse Fourier transform has a different sign. Okay, so this is the way how we get approximate units in L1. And I share now another screen, hopefully. Yeah, and I finish today's course with the following lemma. If you give me any function in L1, so either with compact support, nicely Riemann integrable, or limit of such functions, and I think you should think of any probability density. In the ideal case, maybe you think of a Gauss function. And that Gauss function is having infinite support, but of course it's nicely integrable or so. And this Gauss function is supposed to be normalized. I would say it's nice to think of a non-negative function so that the area is equal to the L1 norm, but this is not important. It can be any function which has integral 1. And then you're looking at an indexed family of all those compressed versions with rho going to 0. So intuitively, you would say, if you have more compression, you're closer to the DRHO. And then the claim it forms an bounded approximate unit for L1. Well, of course, L1 viewed as a Banach algebra with respect to convolution, or as we know, it's even an ideal within the bounded measures, but we just use internal correlation. You could say, if you want, you know Lebesgue integration theory and you know convolution is by integrals of Lebesgue type almost everywhere, but that's not the point. So I have to explain or emphasize a little bit. I'm not talking about a sequence, and that would be the more elementary description. I would say, if you take any sequence rho n going to 0, you would have this. But no, that would mean if only if you're taking sequences, but there are so many not used values rho which are still small and you don't know what happens there. And I'm saying, no, any small value of rho will be good. Well, good in which respect? And that's why we have to formulate it properly. So the claim is, or I hope that this part is written out carefully enough. The goal is, if you're telling me I want to apply this family to a given f in L1, so we're talking about approximate unit for and within L1, and you're giving me any positive number, can I tell you, is it possible for me to find a parameter rho, kind of a quality parameter or a small number, with the guarantee that you can take any rho which is below that parameter, including maybe or not, such that we can guarantee that whatever you take, as long as it is good enough or small enough, then the convolution product of this sufficiently compressed, say Gauss function, convolved with f is epsilon close in the L1 norm. This is something I should correct, in the L1 norm. Okay, and as a first step, I would say we have to look at the functional which assigns to each L1 function the integral. It's either the value of the Fourier transform or the integral. And this is well defined on the continuous bounded functions, and it's easy to see that it's extending in a proper way. So it's a bounded continuous function, which we will need later because we will approximate our g with a function which is not having integral 1, and then we have to adopt it. Now, I hope it's okay if I continue with the proof here. So we have to control the k hat of 0 minus the g hat of 0, which is 1. So you see here, that's the difference. And of course, this is a particular value which is controlled by the sup norm. So it's the sup norm of the difference between k hat and g hat is this controlled by the L1 of k minus g. So we'll see, okay, this term, which will be useful later, will be controlled by some positive number. We have to see how we have to choose the eta. The next thing is that we want to show, and that's a separate lemma, that for compactly supported functions k, the proof is kind of much better. So essentially we would say it's uniformly concentrated and it's uniformly convergent. So you have an L-infinity norm, a sup norm estimate for this. I was doing a separate lemma, so which I have to still insert into the text for the main script. Okay, so the point is, here it's kind of a Dirac delta convolved with f, but with a factor here, and this can be made small by some more elementary consideration. So now we are using the fact that STRHO is a linear operator. So we're saying we have to look at the difference between the convolution action. This is kind of your easy Dirac kernel, and this is the one that we would like to take, where you choose a completely general element. So we use bilinear distributive law. So we put okay, there is an error that f should be a g. So we take STRHO of k minus STRHO of g. So that would be g. And we pull out the f on the right-hand side. And then we use the submultiplicativity of the L1 norm. So we get this expression. But STRHO, as I was telling you, is norm preserving. So it's the same as k minus g. And we can make that, because we know this here, smaller than eta. Now, if you're putting everything together, you have to say, well, I would like to know the given g sufficiently compressed convolved with f minus f. And then, of course, I say, well, but I don't know directly if it's maybe not compactly supported. I replace it by compactly supported. That one might have an integral which is not exactly 1, but close to 1. So, but this term is possible by elementary ways, and this is the correction term. And so at the end, you're finding, I think I was making the assumption that the L1 norm of f can be assumed to be 1, that I get 2 eta plus epsilon over 3, And so altogether I can make it smaller than epsilon. So the key idea is, if somebody is giving you a compactly supported measure with integral 1, and you compress it, you give a function f which is nice and decent, and then you measure the difference in the L1 norm, everything is fine. And then you take approximation, you use density and all the rules that we have. And so in this way, I hope that I have convinced you that I can get approximate units in the algebra L1. And so I have still to tell you why the behavior of the SINC function is useful to get Riemann-Lebesgue, and how all these other function spaces have to be used. Thank you for your attention and ask for comments on the side. So I will stop the